Good evening, everybody. Welcome to the last session of the day, and I'm glad you all made it. I'm going to talk about, so I'm a Java performance engineer. I've been a Java performance engineer for more than a decade. I started as a compiler engineer and moved on to Java performance, so I've been in this field for a while now. Today I'm going to talk specifically about performance engineering. Okay, the methodology, the process, the approach. Okay, my name is Monica Beckwith. This is my second time presenting at Philly ETE, so I'm glad to be back. And a quick introduction. Like I said, I'm a Java performance engineer. I am currently working as a consultant. I work for myself. My company is called CodeCaram LLC. I also work with an industry expert called Kurt Pepperdine, if you've heard about him. And we work we're partners and we offer training in Java performance. Okay, and the company is called Extreme Performance Experts. Prior to this, I worked with Oracle, AMD, and Sun Microsystems. And as a performance engineer, so I've done JIT compilation, optimization, JVM heuristics, garbage collection, and the last title that I had at Oracle was First Garbage Collector Performance Lead. Okay? So like I said, today I'm going to talk about performance engineering and then kind of dive into Java performance analysis. While talking about analysis, I'll talk about the approach and the methodology, okay? And then we'll apply it. I'll walk you through an example, and I'll talk about the tools and stuff like that in the methodology itself. So when we're applying it, we're actually, seeing things in action, performance engineering in action. So if you've seen any of my talks, you know that I rant about how performance engineering should be a part of your system development lifecycle. It should go hand in hand. Your non-functional requirements and your functional requirements should be together from the design phase. So what is performance engineering though? So there are two components to performance engineering. There is the performance requirement, where you also do the test plan development. So you gather requirements, you develop test plans, and then of course there's the whole aspect of analysis. You got the requirements, you have your plan. What are you going to do with it? You're going to analyze it. Okay? So there are two separate aspects of it, and we'll dive into each of them next. So let's talk about requirements first. So of course, ask questions, right? How do you know the requirements if you don't ask questions? So the basic questions are, what makes the customer happy? And then the other side is, what makes them unhappy, right? And when you're trying, so I work with statement of work in my consultancy, and they explain to me the performance issues, and I say, let's come up with a statement of work. And this is what I want to capture in my statement of work, okay? Are there any current issues that need to be tackled? So that becomes top priority. So you try to build your performance plan around that current issue, and then you give out dates or what are milestones based on that, all right? So then so once you have asked questions, then you need to understand and define your measurement requirements, right? So what do you need to understand? You need to understand the quality of service for end users, okay? So when you're working with the customer who has an application or a system, you need to understand what kind of quality of service are they promising their end users, okay? So once you understand the quality of service, you get to define metrics in measurable terms. If I make changes, if I optimize something, a code path or a platform, if I cannot measure it, or if I can't explain to you what I just did, nobody's going to pay me, right? So I have to be able to come up with success metrics in measurable terms, okay? And so that's the definition right there. And those measurable terms become your system level agreements. So these are the things that you agree. As a system, these are the agreements that my system will have. And that's what your performance engineer will go after, okay, to improve those agreements. So then after we did all that, we get to define success. So we get to document, understand, and prioritize your SLAs. So what are the SLAs? That's the documentation. Giving definition on them is the understanding part of it. And then prioritizing. Do you choose throughput over latency or whatever? So I'll talk more about that here. So of course, like I said, the SLAs are throughput. It could be response time, capacity, footprint, CPU utilization. We were talking about, you mentioned that there was an online course that does tracks the footprint of your code, right? So all your classes, how much, it's not just that, not just the classes, not just the code. It's also the footprint, the memory, the garbage collector, right? That's also constitutes the footprint. So on the system that you're running, how much does your Java process take? That's an important part too. So, and of course CPU utilization, how much are you utilizing? There's also power. Some people are more interested in making sure that the power utilization is low. So that also becomes a good metric. So all those things, you're going to make sure that you document, understand, and prioritize them. So, and then you work for it. You work towards monitoring, measuring, and defining performance in terms of all that I mentioned, in terms of your system level agreements, okay? So let's define success. So again, it's the same thing in a visual chart. You have your SLAs in throughput, response time, footprint, capacity management, and availability. So let's start with throughput. So what is the expected throughput? If throughput was your first priority, you need to ask your customer, what is the expected throughput? Now if they say, my expected throughput is like, say, 1 gigs per second, right? Next question is, can you fall below the expected throughput, right? Your system is not going to be able to sustain 1 gigs per second every time. Load will change. You will have spikes. You will have other issues. So the next question, of course, is, can you fall below the expected throughput, right? If you can fall, which everybody will say yes. I mean, nobody wants like 100%. I mean, nobody can deliver that unless you have guarded set of users and guarded set of inputs to the system, right? So how long can you stay below the expected throughput, right? So we can go below the throughput, expected throughput, but how long can we stay there? And what's the lowest we can go? So that kind of information is what helps you better tune the system, right? Then also there's the other aspect of it. I know what I'm trying to measure, but where is the measurement happening, okay? So the throughput measurement, first of all, how is it measured? So for example, are you measuring transactions per second, messages per second, or everything? Or you have a bunch of things that you need to be, that constitute throughput. Where is it measured? Client side, server side, or browser, or again, or everything. You're measuring everything. So if you get these things listed up front, then you and the person that's hiring you, I guess, or the person you're working for, have a clear understanding. All right, we are striving towards the same goal. What about response times? Okay, same thing. What's your expected response time? Can you go above? So what happens if your users double? For example, you're an online retail shop and it's Christmas or whatever. So your users have quadrupled actually many times. So can you go above the expected response time? Because your response time is going to suffer, right? And if you can, how long can you stay there? How many users can get that bad response time, right? You need to figure that out. And how much is that? So you have to quantify, if your response time, how bad can it get? And same thing as measurements. How is it measured? Are you measuring just the percentiles? Are you measuring 5 nines, worst case, or all of it? And I give another talk on this, and it's a rant basically, where I talk about how measuring the right thing and capturing all the information is interesting. People go and talk about average response times, and that just doesn't make sense to me. So if you don't know your worst case, then you're missing that one spike that could bring the system to its knees, or all the systems to its knees. So, and I have, in the talk, I talk about how I was working with the system and they had a 5-second. So one GC pause was about 5 seconds, and they never captured it, so they don't know what brought the system down till we got the log and we figured it out. Anyway, so capturing the metrics is important. Where is it measured again? Client, server, complete loop, very important. And I can go on and on, but I'm not gonna, so I'm gonna skip footprint. I'm gonna talk about just a quick one point about capacity management. So again, what is the expected load? And so not just the expected load, but if you have multiple systems, which usually you do, that's why you're doing capacity management, there's the load balancer issue that people don't understand. So we have to ask questions. What happens is one system gets loaded more than the others. You know, are we designing, are we capable of that kind of increase in load in one over the other? So we got to work with that too. Of course, how is this measured and all similar things. So one of the things that you have to ask is, what's the maximum load that one system and then all the systems combined can tolerate? And how long can they work on that maximum load, right? And what metrics are being captured, of course. All right, so that was the requirements, and then you go ahead and you develop your test plans, and now comes the interesting part, the fun part, right? The performance analysis part. And I'm going to go and talk specifically about Java performance analysis, because I'm going to give some tools and stuff like that. So more, it's pertaining to Java performance analysis. So as a performance engineer, so to me, performance analysis means that we're going to analyze the factors that enable the end user to have an experience that meets or exceeds the quality of service. So when, as a company, I'm promising my end users, like again, online retail, you know, I'm promising a quality of service. As a performance engineer, I want to make sure that all the factors are enabling the end user to meet or exceed that experience. Okay. So we need to. So remember, when we were doing the requirements phase, we understood the quality of service, and then we made our SLAs in terms that we can measure. So in performance analysis phase, that's where you track your measurable SLAs. Okay. So if I had to simplify everything, and I had to make a Java application stack, and I would make something very simple like this. I would have my application and its ecosystem. Then I have my JVM, and then the Java runtime environment. And then that runs on top of the operating system, virtual or real, that's okay. And then, of course, the hardware, the actual thing that's running on. So it could be cloud or whatever, but this is very simplistic, okay? And there's a reason why I wanted to say that. I want to have this very simple thing here. So when I'm doing application performance analysis, I'm just concentrating on the application and the application ecosystem. So basically, I'm interested in either the application services or the application server itself. So I'm doing performance analysis of the application server or the database, which is a part of the ecosystem, or any other services in the ecosystem. Or I could be doing everything. So when I say everything, that means, remember, measure and track the SLAs for all those, right? We're not just having a unified SLA agreement. We're talking about SLAs at application services level, application server level, database, and any other services. So every stage we have different SLAs, and that's a performance analysis. And as a performance engineer, I'm going to measure and track all those. Now, what if I was a JVM performance engineer, right? In my past life, I was. So what am I doing there? So I could be studying and improving class loading stats, JIT compilation. Like I said, I worked on JIT compilation optimization. So yes, we could be doing that. Garbage collection, again, threads, optimizing threads on the host, and locking stats. And I'll give an example about locking in the JVM. What if you're doing OS performance analysis? Again, we have system and kernel stats. We have locking stats at the OS level as well, threads, and so on. And finally, hardware. So when I was working at Advanced Micro Devices, that was my major concentration, was the 64-bit Optron processor. So there we were studying memory bandwidth, the cross-traffic, because it was a non-uniform memory access architecture. So, and then the consumption, and then CPU and core utilization, CPU cache efficiency, utilization, different levels. They have different levels of cache at the hardware. Anything that's architectural specific. For example, if you have a GPU, processing unit, so you may want to do an SLAs, measure and track SLAs for that as well. I/O, of course. So now we know all these things. Now let's go and try to solve a problem. So what are we trying to achieve, right? So if you want to improve the application. So then my recommendation, and that's the approach that I'll take. The approach to take is top-down. So you move from the top, which is the application layer, to the bottom. All those things will be called the platform. So the application sitting on top of the platform. So it doesn't matter you're running on the JVM. Of course, you need, when you're doing the application, you have to understand the language, right? Other than that, what doesn't matter what's happening underneath. What really matters is we're concentrating on the application. And then the process is very similar between top-down or bottom-up approach. The process of performance analysis is the same. Step 1, monitor. Step 2, profile. Step 3, analyze. And then tune and apply. So this process doesn't change. It's the same for top-down, bottom-up. So this is the methodology. This is what you do. You monitor, profile, analyze, tune, and apply. And that's where you're tracking your SLAs. As your SLAs improve, you keep tracking them, and you keep on redoing this process till you reach the level of satisfaction to improve that end-user experience. So what if you're trying to improve the platform, right? That's where the bottom-up approach comes in, okay? So your platform could be improving the hardware. You're working for, like I said, Advanced Micro Devices or Intel. You're trying to improve the hardware. You're working for Red Hat. You're thinking of the OS level improvements. You're working for Sun Oracle. You're thinking of JVM GRE level improvements. So that any of those constitute the platform. So you're trying to improve the platform. So you're going from the bottom-up approach. And I'll give some examples for both of them. And like I said, the process is the same. Step 1, monitor, profile, analyze, tune, and apply. So let's talk more about top-down approach. So basically, top-down approach, you choose top-down approach because you have the power. You have the power to modify code. Okay. At any level, whatever you're trying to optimize, if you do not have the flexibility of being able to manipulate the code or don't have the sources, then what you're doing is just essentially just looking at a black box and just saying that, okay, this could have been optimized, but I don't know where I'm going to optimize it. But that doesn't work for top-down approach. You have the power to modify the code, or rather, you should have the power to modify the code. So any kind of improvements that you're making, you're directly making it into the application code, or if they say, or a benchmark of it, or whatever that you're working with. But you're able to see the benefits. You're able to apply and improve the SLAs. So for top-down approach, like I mentioned, anything below the application layer is considered platform. So your application should work on platform A, and if it's the same language on platform B, it should work better. So it's not just because on the system it's working better and you have met your SLAs that you're done. No, that's not true. Your SLAs should be met on any other platform that can be replaced with this particular current platform. Okay? So it doesn't matter what's there. What matters is the application that's working efficiently. Okay? So let's talk about monitoring. So while we're doing the top-down approach, you're monitoring your system under test, right? And then, so what is monitoring? So there are tools, like they call it APM tools, right? Application Profile Monitoring tools. So there are two types of APM tools. There are active tools and passive tools. Active tools, they create alert. So you have thresholds, a bunch of thresholds, and whenever those thresholds are crossed, you get an alert. So these are actively monitoring for those thresholds to be crossed. Passive is like something like network taps. They're always monitoring. It's just tapping into snooping and getting information. So it's always monitoring. I like to add something called offline. So working on the platform as a platform performance engineer, I know of offline monitoring too. And I bet everybody else knows it. And they're called logs, right? So you can, once you run and it's running and it's in production, it's on, but you can go offline and see those logs because they're dumped somewhere, right? So you can do your own human monitoring, right? So what tools do we have? So right here is what I have mentioned that's freely available, okay? So we have Visual VM, okay? And then we have something called Java Flight Recorder, which is built into the JVM. Then, of course, when I talk about offline logs, you can look at the compilation logs by that option called print compilation. You can look at the garbage collection logs with print GC details and print GC date stamps. And then you can look at class loader statistics with that jmap-cl stats. The jcommand GC class stats also gives you similar. So there are lots of options for these to be able to generate logs so you can visualize and monitor your application, okay? What about monitoring on a Linux platform, right? So like I said, the platform, when you're monitoring the platform as a whole. So if I was working on like the JVM plus Linux, I would also monitor MP stats, sysstats, and VM stats and stuff like that. If I was working on, and then I would also go ahead and check on a Windows box and make sure that I'm looking at perfmon, task managers, and other things, okay? So monitoring, even though I said platform is a big box, you need to be aware and you need to monitor at every level so that when we swap Linux with Windows, we're still being able to do these active monitoring, okay? What about profile analysis, right? So now we have all the data we need. We have collected all the logs and we have got all the alerts and everything, right? So then you have to sit down and identify areas of improvement, okay? And then profile those potential hotspots. So that's what is analysis and so profiling and analysis right there. So remember, I spoke about the alerts, right? So if the alert told you that, hey, there was a GC pause, okay? That was more than your acceptable, so max pause that you wanted was 1 second, but you had a GC pause of 1.15 seconds. So that's an alert comes in, and then you say, okay, now I need to go look for areas of improvement. So I go and profile and figure out what's going on with my application, and then I analyze, okay? So what tools are out there for profiling and analysis? So what I've listed again are free or open source or GPL, BSD licensing. The one tool that I use more often than anything else is the Oracle Studio Performance Analyzer. There are also perf tools and PAPI and CodeXL from AMD, I think. dtrace, of course, people who worked on Solaris, dtrace is also on Linux now. O profile, of course, which is Linux, gprof, and all those things. For Java application monitoring, you would again use Visual VM or the NetBeans profiler or JConsole. Lots of people still use JConsole, and it's a good tool as well. So then comes tuning. You analyze, you found your hotspot, you found out that the hotspot is in the JVM GC, for example. So the simplest tuning would be, of course, it's not always that simple, but at least to start with, select the right heap and the right GC algorithm. Sometimes that's all it needs. Sometimes you are using a latency-sensitive garbage collector when you should have been thinking about the throughput garbage collector, which is the parallel collector in OpenJDK hotspot. So if you're doing GC algorithm and you're trying to optimize the garbage collector, you have to make sure that the objects are aged appropriately. What that means is that most of the garbage collectors in OpenJDK hotspot are generational. So since the principle is that most objects die young. So you try to age them in something called the young generation, and then once they age, you tenure them into the old generation. So that's what it means, age objects appropriately. So if you age them well enough, most of the objects will die in your young generation, and you won't have to do expensive old collections. And the second thing is also based on the generational design, which is promote only long-lived objects. Don't promote things that are going to die. Just let them die in the young generation and only promote long-lived objects. And then there's options of, because there's some stop the world events, which means that only the garbage collector threads are running, your application threads are stopped. So you want to make sure that the stop the world events happen quicker. So you could add more GC worker threads per virtual machine that you have. When the garbage collectors are working with your application, then that's called concurrent work. So GC also works concurrently, some of the GCs, and they also have a work thread count. So try to see if you can optimize that. Then there are other optimizations at the JVM level, right? Which one of them is called compressed tubes. So if you're using a 64-bit operating system and a 64-bit JVM, and people know about 64-bit applications, I hope. So there's something called compressed tubes where the ordinary object pointers, so it's all about pointers, right? Pointer manipulation on the heap. So those pointers are compressed to 32-bit. So these kind of tunings go with the JVM. And then there's also some things called always preach. So there are different. What I'm trying to say is that when we know what we're trying to optimize, if the JVM and garbage collector is what we need to optimize, then we have different sets of options that we can use with the application. So tuning, you could tune your code to meet or exceed your SLAs. Make sure that you have appropriate ramp ups and ramp downs. Basically, you're trying to see and trying to keep your code in steady state most of the time. So for that, you have to try to see what your steady state is. If your steady state is always working at 90% utilization, something doesn't seem right? So if you can figure out how to achieve a steady state that can account for spikes, 10 to 20% more increase in your usual steady state, then that's a good design of an application or good rework of your application. So again, if you move away from the platform, object retention is very important even for application. Garbage is not that important. Object is, creation is, right? So object agent retention is an important thing, especially if you're doing Java performance analysis. So understand what forms your live data set, what stays longer, stays live longer. Like for example, your cache. You're trying to do some transactions and you have some cache. That's going to live longer, so you have to be able to account for that. You need to understand that kind of information from your application. What is your application doing? And then confirm you're measuring the right thing. You think, sometimes you may think, and one of the examples that I have here, I thought I was measuring the right thing, but I forgot that there were certain optimizations enabled by default in the JVM, and I forgot to turn it off, just because I wanted to do this experiment. So you have to make sure you're measuring the right thing. Let's talk about bottom-up approach. So bottom-up is when you're working on the platform and you're looking up towards the application. So I don't have the power. I need the power to stress the platform. So basically, I know the changes that have gone into the platform. I'm very conversant with that. But I need to stress that now. So I need to build an arsenal, right? So that's when you take the bottom-up approach. Again, I'm working somewhere in the platform, and I need the power to stress that. So I'm going to still stress it by my application or benchmark, but I know everything about one of those platform layers, and I know nothing about anything else. That's what the bottom-up approach is all about. So where do we start? So first, know what you're stressing. Then you get or write the appropriate application. So if I'm stressing the JVM, for example, JVM is a platform, and then I need to get the right benchmark to stress the changes that were made to the JVM. And then the tools. You have to be able to look into the JVM to make sure the changes actually made a positive or a negative impact, right? So for example here, I'm stressing CPU. So you got to make sure that you're doing all these things, and that's what we used to do as performance engineers at AMD. We used to gather performance counters. So at the hardware level, to be able to see what's happening, there's something called performance counters. So performance counters for CPU information, core stats, cache hits, misses, branch predictions. There's something called load stored unit. Out of order execution, if that's your pipeline. So all that, you should be able to measure that. What if you're just talking about memory? Again, gather information for memory utilization, memory bandwidth, read, write. What I'm trying to say is that don't try to think, oh, I'm just doing memory, so bandwidth is the only thing I need to measure. That's not true, because there's so many things that happen. There is the read-write. So I was working with some other people that made these changes, and they were trying to do this memory expansion using flash-based memory. What they failed to mention to us is the write traffic, the write bandwidth was obnoxious, right? So as a performance engineer, it's my job to make sure that I check the max read bandwidth, max write bandwidth, not just memory bandwidth. Of course, if you do more read operations, your memory bandwidth is going to shine. But the problem was with the write bandwidth, and then as a performance engineer, it's my job to point that out, or to figure that out. So you need to analyze all that. I spoke about JVM GC. So for example, G1 GC was very new, right? So as a performance engineer, what did I need to do? I needed to, first of all, understand what the garbage collection was doing, right? There were different phases to the garbage collection, so I needed to understand all the phases. There are different, like I said, for stop the world, there are different threads that we can add. So try to figure out the work queues, try to do figure out the concurrent work and how much pressure it can put on the application. Because remember, concurrent garbage collector works with your application on the same system. So now you're sharing resources. So you got to figure out the work pressure. There are internal queues, there are internal thresholds, buffers. So all those things, as a performance engineer, need to understand all that. So what do we need next? Know what you're stressing, we did that. We talked about writing appropriate workload, and we talked about getting the appropriate tools. So let's have some fun. Let's look at let's walk through a performance engineering exercise, okay? So building a problem statement. So for this particular exercise, I chose to do the bottom-up approach, again, looking from the JVM. So in Java 9, JDK 9, there is an improvement to contended locks, the JVM locks, okay? And for all these things, there is a process called JEP, so JDK Enhancement Proposal. So the JDK Enhancement Proposal stated that it wanted to improve the performance of contended Java object monitors. So contended being the term here. So in the past, there have been optimizations to Java, I think in Java 5 or 6, to uncontended locks. And it was called bias locking. If people have used the JVM and they have enabled bias, now it's enabled by default, I think. But in the past we had to enable it on the command line. So bias locking is for uncontended locks. This particular optimization is for contended locks. And this is only in Java 9. So like I said, I want to build a problem statement. So first I need to know what is contended locking, right? So if a single thread T is executing a synchronized method, and then a different thread U wants to come along and enter the synchronized method, which is already locked by T, we have what is called contention, because T already has the lock and U wants to get the lock. So that's called contention. Okay, we still have time. So what happens is that if people are familiar with locking, even at the operating system level, we always talk about thin locks and fat locks, or inflated locks, or heavy weight locks. So when I'm talking about contended locks at the JVM, I'm talking about heavyweight locks, which are also known as inflated locks. Okay. And then the object monitor maintains a weight. So that's a difference. So when we're talking about locks, we're talking about inflated locks that have object monitors. Object monitors will maintain weight sets of their own, okay? And then this weight set will contain the threads waiting for the lock, right? Very simple. And then, okay, so now, yes, cool. So if I had to explain it, this is what I would draw. So we have the enter and exit operations. We have a queue right there, and then we have a wait queue on the left, okay? So anything waiting on that object monitor will go into the wait queue, okay? So what is a wait set? It's basically a set of threads. These threads are waiting to get that lock on that monitor, right? At the beginning, of course, hopefully you're not always contended. So in the beginning, it'll be an empty set. And for every object, just as you have a monitor, so every object has an object monitor, similarly every object has a wait set. And then to be able to manipulate the wait set, I'm not going to go into details about all that, but to be able to manipulate the wait set, you could use object wait, which means please wait, simple, suspend. Notify all is when you want to get one of the threads to come in and work on the monitor. So now if I put the text, so when I say wait, or not me, but the object monitor, if you get a wait signal, then everybody goes into the thread goes into the wait queue and starts waiting till it's notified. Once it's notified, it comes into the object queue and then takes over the lock. Very simple. But so that becomes a problem statement. And when we're trying to measure the improvements, we need to know what we are stressing. So here we go, know what you're stressing. So I'm just following the rules that I had highlighted earlier, right? Problem statement and then know what you're stressing. So if you look at the JEP, there are some speed up targets there. So I'm listing a few of them. So they say that the Java monitor enter operations are made faster. Java monitor exit operations, remember I said enter and exit right here? enter and exit. So those operations are made faster. And then the notify as well, which I've not included here because I don't have time to cover it. So Unpark is a part of exit too. So that particular event has been made faster as well. So we'll go verify that. Now, to be able to verify that, first we need to have a tool that stresses that, a benchmark that stresses these things to be able to measure them. Remember I said you have to have your SLAs in measurable terms. So how do we measure these things? We get right or we get a workload. So in this particular case, the JEP, the Java Enhancement Proposal, has a list of benchmarks that they use for stressing the contended locks. One of them is by Doug Lee, and in the simplest form, it compares multiple locking techniques. And for us, we just need to figure out the contended locks, right? So we just are interested in this particular section of the benchmark. And what we're interested is in the synchronize this instance, the instance method, right? That's all we care about. We're going to make sure that's contended. So again, if I know what I'm stressing, and I said I made that mistake earlier, that we have to make sure that we're actually going to measure what we think we're going to measure. I know what I'm stressing, but am I actually measuring the right things? So in this particular case, bias locking was enabled by default, so I had to make sure that I disable bias locking. And I also wanted to make sure that, remember I said contended locks are inflated locks? So I want to make sure that I'm not getting any stack-based locking. I want to, in fact, get inflated locks, okay? The fat locks. I want to get to the fat locks. So I have to use heavy monitors. So basically, I have to enable that. So every time it gets to using heavy monitors, which are the fat locks, inflated locks, okay? Next, we want to be able to get the right tool. So since I'm working with the JVM, I had given, in a couple of slides earlier, I had given you a list of tools that are my favorite, right? And those are all free, open source, freely available. One of them is the name just changed. It used to be called SSA, so it used to be Solaris Studio Analyzer. Then it went and they called it Solaris something, and now it's called Oracle Developer Studio Performance Tool. And when I go to the demo, I'll click on that link, and so we can see more about that. But what I wanted to show is that the way the tool is divided, there's a collector phase of the tool, which collects information while your application is running, and then you can analyze or look at the collection, the experiment. It's called all the things that it collects are called experiments. So you can look at the experiments using something called analyzer. Okay. In order to be able to collect, I have put in some options here. If yours is a Java application, the tool is smart enough to figure that out because JON is enabled by default. Again, the clock profiling is enabled by default at 100 samples per second. Heap tracing, if you want it, you can enable it. It's not enabled by default. You could set a time over which you want to collect the experiment. You can say that. And then if you wanted to do hardware, remember I talked about performance counters with respect to the memory and CPU information. You could find out more about those performance counters and how they're, for example, cache, different cache levels at the processor level, how that affects while you're running a benchmark. You could look at the hardware counter profiling information, which we're not going to do. We're going to just do the simplest one, the clock profiling. So then observing the improvement targets. So before, like I said, before I go into demo, I wanted to show you how the changes. So I went and did the experiments, and I have some observations here. So I've summarized them here. So the first thing is Java monitor enter operations. So usually, if I had to draw a flow chart or whatever, once a runtime finds an inflated lock, it enters into an object monitor, and it also does a method called object synchronizer. Usually it's the slow enter. With Java 9, there is something called quick enter that's added to the code, to the runtime. Okay. So this is a snippet of the tool, and what you see is a caller-callee stack. So runtime stub complete monitor locking Java calls the shared runtime complete monitor locking C, okay, and that thing calls these four, like object monitor enter, object synchronizer quick enter, object synchronizer slow enter, and then handle marker clearer, which is not that significant, but those three are, okay. So we'll look at all three of them. So what the tool gives you is information on every method in user or machine and expert mode. But I may not, what it simply is that if you're more comfortable with the application, you know more about the application, you think the JVM system is a black box, you can just feel comfortable in user mode. You don't have to go to any other mode. As a JVM engineer, I feel comfortable in getting a mixed information, like expert mode. Some people who are platform engineers at a hardware level, they may feel more comfortable looking at machine code. So they may want to go into machine mode, okay? So, but I may not have time to demo all that. But so another thing that the tool gives you is like each method. So if I'm a method A, and I have two callees, method B and C, so it gives you inclusive time. So method A's inclusive time based on all its callees. So it'll have method A's time, method B's time, method C's time, all inclusive, or just method A's time, which is called exclusive time. So how much does just method A by itself take? How much does method B by itself take? So what you see on the top is exclusive time. So the object monitor enter, remember I showed you the caller-callee stack? So one of them was, the first one was object monitor enter. By exclusively, JDK9 was faster. It only took 8.7 seconds. And this is because I have kept that thing in a loop, right? And then on JDK8, with the same loop was executed, it took 14 seconds. So it's just the exclusive time by itself is higher with JDK8. With JDK9, inclusive time, that means object monitor enter and anything else that it calls, even the inclusive time is better with JDK9. It's only 18 seconds versus 26 seconds on JDK8. So with JDK9, like I said, the quick enter was a new addition, right? So as you can see here, there's no time spent by JDK8 because JDK8 is not even available. The libraries, the runtime, the code changes that went into JDK9 were not available for JDK8, so of course it didn't spend any time. It's a new entry in JDK9. And then the slow enter, remember the default path that everybody would go for inflated locks? That also has improved because JDK9 spends less time in it, right? So it's now 2.4 versus 6 seconds, and the inclusive time is 7.7 versus 11 seconds. Similarly, exit operation. I just want to look at the time quickly. Okay, so exit operation there's three things. There's the exit epilogue, and then there's unpark and all these events, okay? I'm going to conclude this and then we probably switch to the experiments. But these are the things that I used to research the bottom-up approach that this example basically, because I had to refresh on synchronizers and stuff like that. I'm going to try to keep it up there. Let me see if I can get back to it. Oops, it went back. No, don't. Okay, I'll come back to it. How about that? Because I want to do this thing here. Okay, so this is the analyzer tool. So I don't know how clearly we can see back there. Okay, so it's not that clear, sorry. But what you see is on the left two are your exclusive times, and then the next two are your inclusive times, and you have a bunch of methods, okay? And what you don't see on the top, it got cut off for some reason. Maybe I zoom out and, oh. Well, Well, you really cannot see that because it's cut off for some reason. There you go. Okay. So what you would have been able to see was this thing here. See, I was talking about different modes. So you have the user, the expert, or the machine mode. And when I summarized my observations, I was talking about the OS platform event Unpark in expert mode. We could also go to the machine mode and we'll look at different things. So for example, we looked at enter, right? Or object synchronizer. Yeah, we could look at object synchronizer, which is, since it's runtime, it's only available in machine mode, okay? So right there. So slow exit, right? So if I did caller callee, so this is what I had showed in to inflate and all those things. So how do we take how do we start an experiment? So this particular thing, since it's a virtual machine, this experiment was run on a different system, and I'm just showing you the experiment on this virtual machine, because in the past I've carried 2 different laptops, but I think this is much better. So, but what I wanted to show you is, if I can find my mouse, there it is, slowly, there you go. Okay, so basically right there, the experiment is very simple. So you have your path of where your collect tool resides. Since I said that it already knows that it's a Java application, you don't have to say JON, and I said that I'm okay with the default clock profiling rate. So all I had to do is put the collect tool in the path, prepend the path with the collect tool, and then I gave a bunch of my options, and I made sure that bias locking was disabled and heavy monitors were used, and that's the lock loops benchmark. And I said how many threads, how many iterations, and how many loops or whatever. So it's very simple. And then to start the analyzer, it's the same thing. It's basically, instead of collect, you say analyzer, and then you start the GUI, analyzer GUI. Okay, to be able to open. So right, what you see over there is a compare experiment mode. So basically, yeah, there you go. So when you start the analyzer, you see something like this. You could either create the experiment from the analyzer itself. So basically, the analyzer is included with the collect tool is packaged. So you could say profile application or profile a running application, and then you could open experiments. So I had a bunch of experiments. You could open any one of those, or there's an option called compare experiments. So you could compare experiments, which is what I did. So I tried to compare JDK 9 results with JDK 8 results. And then you could connect to a remote host too. So if, for example, if my experiments were on a different system, I could just connect to that system with my GUI running on my system. So we could do that too. What else is important here? I already spoke about caller callees, the call tree, but we cannot see it in comparison mode. But if call tree is very important. There's a timeline. So basically, each of your threads, your garbage collection threads, your application threads, everything that's running on the system, you see this kind of output in the timeline. So, for example, if I know that the GC pods was very high, okay, so I can go to this timeline. I can collect the GC event, basically, because remember I said GC date stamps and timestamps and all those things. So I can match the timestamp to these things here, and I can see the call stack of what it was executing with my garbage collector. So if reference processing was a problem, it would show up here. Then you can look at the source and disassembly as well. So let's see if it'll show up. Yeah, there you go. So this since we were in machine mode, I guess, so we can see something that's called the x86 assembly, x86-64 assembly. And then you see whatever. So the orange things are your hot paths, hot code, so basically something that's executed and has collected some time samples over there. So push and move, for example, there, and object synchronizer, inflate. Was what we were looking at. So it's a very interesting tool, a very helpful tool for me as a performance engineer, and I think We could talk more, or I'd rather take questions if you have any. I can talk more about the tool or anything else. Whatever you guys are interested in. I can go this too. And go to the. There you go.
Do you take a different approach between a production type of monitoring or profiling and a development? How would you go about it?
So when I'm doing profiling, I already know what I'm looking for. Okay, so what happens is all profiling tools will add an overhead. Okay. I'm okay with people using print GC details and print GC timestamps in production. I'm not okay with people collecting and sending me samples from production. So I'd rather have them replicate it. What that helps replicate their workload on some other system. What that helps with is not only making sure that it's reproducible, right? And also I can spend some time on the system. Many a times I've tried, and I'm not saying this, any profiling tool comes with its own sets of learning, like a learning curve. Many people are comfortable with using, I don't remember the names of the tools, but this particular tool, for example, has so many different views that I, as a performance engineer, feel very comfortable in or they can collect an experiment and send it to me, and then I can just do a remote access to it. But yeah, you shouldn't be using any profiling tool in production, actually, because that doesn't make sense, especially if you're concerned about performance, doesn't make sense, because it definitely adds overhead, anywhere from 5%, depending on how long you're profiling, to about 25%, even so if you're collecting a major hour-long window. Yes?
I only asked because right now we're having a garbage collection issue, and it only happens under heavy load or after many days of just work. It's a web app, and I want to be able to text my guy and say, hey, do this.
Yeah, but for that, you just look at your GC logs, garbage collection logs, to begin with. So if you haven't enabled print GC details or print GC timestamps, then you should do it right now, and then make sure you enable it in production. Redirect a log to say X, I think it's X log GC or something. Just redirect it somewhere, and then go look at it while it's in production, and that's going to be, so match the timestamp. So you said it happens after 24 hours, for example, right? So you have the day, and then you have the hour, or you could do GC timestamps, which will just give you timestamps from the beginning. So if it's 24 hours from the start of the process, for example, so you know exactly where it happened, so look at the GC event then, and then kind of, that's doable, definitely. Application profiling happens when GC is causing, or something else in the application is causing GC issues. So you're doing a lot of reference processing, for example, in your application, and that's, causing GC stop the world pauses to have a longer time. So you're trying to correlate between a couple of things, and that's where application profiling is really important. Garbage collection by itself, you can just look at the logs and you'll be fine. Yeah.
Is there a place where, so I've started jars with JVM parameters. Is there a place where those JVM parameters, like a config file, are globally set?
It depends on what server or whatever you're using. Tomcat will have its own different set than any other app server of yours. Are you talking about something that this tool does, or are you talking about, because everybody will have their own config file, so to speak, or a repository where they can add to that?
But there's no, I guess I'm asking that there's no global JVM defaults?
Yes, there is. There are. So there's something called globals.hpp, but what you could do is use this option called XX plus print flags final. So it tells you after you have set a bunch of flags on the command line and what the default flags were. So it'll give you a combined list of all the flags for your virtual machine. Yes, so it's called print flags final. So if you don't want to look at the source, but because sometimes you can change things on the command line and that will affect some other things. For example, if you specify a ratio for the young generation, that means your nursery sizes vary. The Eden and the survivor sizes will vary. So if you do print flags final, it'll show you the ratio and also show you the new size for your nursery. Yes?
Just for the recording.
You can just yell from there.
In your,
Oh, okay, sorry.
I would imagine that most of the performance issues are in application code. Someone has done that for, I guess you've done like performance analysis of application for a long time. Do you find that that's the main place where most of the performance problems originate from?
I cannot say that because I've also done JVM performance analysis for a long time and also at the hardware level, for a long time. So it depends on what you're working with and what flexibilities you have. Remember when I said that application code should be accessible? Same thing goes with JVM and GC. You should be able to tell. You cannot tell. You can always blame, right? But you cannot go to the bottom and find out what exactly is the problem. So people always can blame the garbage collector and say, oh, my application is doing something, but the garbage collector should have been smarter. If I'm creating so many more objects, the garbage collection should have known about that. So most of the time that I hear complaints are about the garbage collector, actually. Even if I'm working with the application, it's more about, the garbage collector should have automatically resized the heap when it knew that there were so many more live objects that should have gone and been promoted into the old generation. Yes, it should have, but you know what, at that time it was not doing for some other reason because you had maybe overloaded the command line or something, I don't know. But yes, but to be able to find out if it was the garbage collector, you want to have tools like that. Yeah.
We recently had a problem where we were leaking metaspace.
Mm-hmm.
Is there a good tool to analyze that? Because we looked at JVisual VM and...
Did you look at I had some J command or whatever, it gives you class loader stats, that didn't help either?
No, because it ended up being a missing jar. So every time we tried to instantiate one of those objects out of the missing jar, there was actually a try-catch around it. We caught it. So we just kept on going,
So how to find the missing jar, I don't know there's an easy way for that, but to be able to just figure out that you have a problem, you can start doing class unloading. There are commands that do class unloading at the JVM command line. So every time you unload class, if it's not really going down and you have class loading issues, it'll keep on, your metaspace size will keep on increasing. That's how you know you have a leak. Right, and eventually it'll go beyond a certain maybe. Right, so it's still right. So yeah, that would be a difficult thing to figure out. So there's no such tool that gives you. Memory leaks are by itself. If you look at that, they're caused by GC roots, right? If you have problems with GC, so garbage collection works. Based on whatever is live in its roots, and then it goes on going from one to the roots, whatever, like a tree. So the easiest way to form or figure out how a memory leak happens is to trace the garbage collection roots. I think that's what you eventually ended up doing, trying to figure out your...
metaspace doesn't get collected.
It does. It does. Your class loader is done, and then it does get collected. Yes, it does.
So where would you see that?
In Visual VM, you'll see the collection happening. You can do class. Yeah.
Even if we force a GC, there's no.
Well, what option did you use? So you have to do class unloading option.
Recording. It's from JVisual VM, there's a button, force GC.
Oh, no, not that. Yeah, it has to be on the command line. It's called enable class unloading with concurrent marking or something like that. Yeah. In my GC talk, I specifically call that option out because you're not the first one to have that problem. So I've specifically called that. Some people will ask me if they look at the talk out of context and be like, what does this have to do with concurrent marking? I said nothing, but then people have problem. As a performance person, it's my job to tell them that you got to use this option to have class unloading while concurrent marking is happening. So that's an option. It's called class unloading with concurrent marking.
And then you'll be able to see the root.
No, you won't be able to see the root. The root is set is for you to. How do you know the root set?
Well, our problem was we couldn't put into Metaspace and include fields without bounds. No way to visualize it.
I don't know if Visual VM. I don't know where Visual VM is right now. But you could. I don't think you could see into. I don't think you can see into the Metaspace. How were you with PermGen? Even that should have been the same problem. You didn't have problem with PermGen.
We're flying 7 and then 8 this would happen. We were stuck for a while. It was literally trial and error from this guy.
Interesting.
We're looking for a Metaspace viewer.
Well, there are lots of garbage collector viewers, and there's one on GitHub that talks about the object and how the promotions happen. I don't know if they include Metaspace in that, though. So, yeah.
So it's growing and
Interesting. Well, I work with memory leaks, especially class loader issues. But the thing is, like, when it comes to me, they have already told me that they have tried all these things, so it's kind of easier for me to just try a couple more and that's it, For you guys, you had to try all that, and finally got it. So yes, I understand it can be a big pain. Yeah. I don't think Visual VM has the ability to view it at all. It just, it's true. You could also look at the active versus, like after garbage collection, you can look at the active classes or whatever too. You do that?
see class stats and
Yes.
the before and after, read this. And
Okay. Yeah, but I think Visual VM lets you do that too. That'll help. I understand that, yep. That is a problem. That's why I get paid, Okay, any more questions? Okay, cool. Thank you guys for being here.